Thanks to the organizers, and also special thanks to Greg to invite me for this event. 3-4 years ago, I think I met Greg in a similar event in Munich. So, and it's always, that was a lot of fun to meet a lot of engaged people in a kind of intense setting, intense interactive setting. So I will try and keep this presentation like relatively broad and non-technical and short as well, so that like if there are any questions that come up or discussion topics, then we can actually discuss them in some detail. So introducing a bit of myself, like I currently work at Zaha Hadid Architects as the head of Zaha Hadid Computation and Design Group. I'm doing my PhD at like Block Research Group in ETH in Zurich. I also teach at the Design Research Lab, which is a master's degree program at the Architectural Association in London. And I've previously studied at the University of Bath and also from the Architectural Association, and prior to that in India. So, I mean, when it comes to you know, complex geometry and complex buildings and the use of technology, like Zaha Hadid Architects like are kind of known for these kind of buildings that are, particularly this one that was completed last year, along with this one, which was also completed at the same time in 2019, towards the end of 2019. And so we have a track record of like, and also high levels of comfort with the kind of BIM that is needed to design and deliver these kind of projects, because we've been doing that with increasing frequency since Zaha's passing 4 years ago. And also things have been in development for at least 20 years prior to that. So we are very comfortable with this kind of workflows and tool chains and delivering complex geometry in a time and budget efficient way. But so building on that, like today I would like to kind of talk about how we are kind of adding in the layers of like research and like, you know, making BIM fun and also relevant to contemporary technological advances in other fields, like particularly computer graphics and cloud computing and so on. So that's one ingredient that we want to add to our capacities, and at the same time we want to leverage these increased capacities to start addressing like other pertinent issues of the built environment, things like housing, things like sustainability, and so on. So in a technical sense, like you know, adding like the research component, like frameworks like Compass from the Block Research Group in ETH, which is a research-based framework, onto the BIM frameworks developed by like companies like Bureau Happold and like Autodesk and so on. Visually, so this is what it means, like looking at emerging research in structural design, efficient structural design, like processing of geometry, you know, interesting topics of origami and how that might affect in manufacturing and so on. Combine that with like, you know, everyday BIM, business as usual kind of BIM, which most of you would be aware of. And again, this is not anything particularly new, like even in the pre-computer era in the 19th century, like, you know, architects like Gaudi were able to focus on the expressive aspects of spatial design, like here on the left, building upon lots of knowledge of other people and establish protocols of design using geometric methods like these on the right. And further, even construction economies were already building on such knowledge, which was encoded into manuals, into documents, and also into ways of drawing construction drawings and instruments to draw the geometries without knowing the mathematics behind it. So there was an entire ecosystem of like such built up geometry based knowledge, which is what we are kind of engaging with. And this is also very true in other fields which are making rapid progress, where like computer graphics and movie making, digital movie making, where there are like several PhDs worth of technical research, which is in the background, operating in the background of like the actual storytelling, the lighting design, and so on. So two main ingredients to this, like that we are borrowing from history and also from other disciplines, is like how do you construct a agile team, first of all. And so in that sense, what we do is my team, like, which is about 11 people, and Zaha Hadid Architects is about 450 people. So like the 11 of us kind of do a range of things, including project independent research, project-based applications of those research. We also do a lot of exhibition and press related work, and also talent development and acquisition and network development. So primarily how we just focusing a little bit on how to build talent and networks. You know, 10 years ago, we went to India, like to do our version of the AEC Hackathon. We went there not knowing anything about like how to build, not knowing what the supply chain is or where to source materials. So in 10 days or 2 weeks, we kind of designed and built this fabric structure, including finding the tailor, including finding the rebars and all the masons and so on. And literally this was all the drawings that we made. So here's the design drawings on the top, and the unfolded fabric drawings, and the pipe bending drawings, and the reinforcement. And so that's all we needed to construct this complex geometry object, which was like, which revealed something to us in the sense that like we can be very, very lean if we know what we're doing and if we work with like the production process. So it was easy to describe the geometry because all you had to do was stitch the fabric and stretch it. And so when we, alongside like in London, where there was like real buildings being made in a similar way, where you bend pipe and you stretch fabric. In this case, it just happens to have insulation, and it also happens to be double layered and so on. It's better engineered, better made, but the principles are the same. So that's why we focus a lot on these kind of hackathon type efforts, because literally that's the backbone on which we build a lot of our tool chains, a lot of our downstream project applied kind of workflows. And another benefit of this kind of hackathon that like we do one almost every year is some of our colleagues and peers like from the team have now left and started their own companies in entirely different fields. Like two of our colleagues are now making robots. And another colleague of ours is now working in the animation industry in a company called Double Negative. And a lot of our collaborators are equally kind of agile and like kind of inventive and resourceful. Like, for example, Yele and Asborn, who started a company 10 years ago by just sourcing robots from Detroit, secondhand robots. And now they're traded, a publicly traded company. So, and also it allows us to convince others like Johannes, who's started a concrete 3D printing company in Austria, that you can do these startup businesses relatively simply, and that like a lot of the architectural knowledge and software making knowledge can be applied to make real use cases, and so So you don't need to make like heavy investments to start these kind of businesses, which are like entirely super digital businesses. All of this is kind of based on an agile framework, and particularly a geometry-based framework, because it's easy to communicate geometrically, visually, than numerically. So that's why we built like a lot of our tools around simple geometric algorithms and visual reasoning. So as research topics in terms of manufacturing, we've been always interested in thin shells and textiles for the last decade and a half. We've also been interested in origami and sheet metal manufacturing and sheet material manufacturing, particularly curved origami. And we've also been interested in all kinds of 3D printing at all scales, like high resolution polymer based 3D printing, large format plastic 3D printing, and also concrete 3D printing on which I'm doing my PhD at the Block Research Group. So all of this is like kind of enabled by what is called the so-called architectural geometry. In simply put, architectural geometry is just geometry that is aware of its structural performance, and it's also aware of how it will be manufactured downstream. So while you're designing, you're already aware of like what are the critical manufacturing constraints. So in other words, it can be considered as a kind of vertically integrated design and all the tool chains. So from design to production, you're already thinking ahead of, so you're not arbitrarily designing some shapes, or you're not designing to fixed a catalog of parts. So just to illustrate this workflow and these ideas, like I will take the latest research prototype that we did with Block Research Group again in Mexico City, along with Architecture Extrapolated. So 3 teams working in 3 different locations before Corona, 1 in London, 1 in Zurich, and 1 in Mexico, start to finish, like 2.5 months, built in a pit inside of a building where the only access was that little door. So we had to bring all material through that door over there. And what this project shows is like, you know, it builds upon the ideas of like seminal people like Felix Candela, who showed that like very thin, structurally effective use of concrete or shapes which are doubly curved use very little concrete, very little material, but can support like a large amount of weight. Like, so that was, and at the same time, he was able to consider how to make these doubly curved shapes with simple ruled geometries. So that was, he based his entire career on such hyperbolic paraboloid geometries, because they were both structurally efficient, therefore materially efficient, but they also could be made relatively simply using straight formwork, ruled formwork. But at the same time, because it was based on formwork, which was thrown away, they were elegant shapes, it was beauty at a price. So this particular project that we did in Mexico City builds upon that idea that like, how can we just get rid of the formwork? How can we have like lost formwork? How can we have like textile formwork? So this was the outcome. So we shipped the textile through that door, stretched the fabric, and then cast concrete. And so it was relatively, and this was like untested technology before we made this. It was it was like my colleague at like the Block Research Group, her PhD research in knitting, using a simple knitting machine to knit all the formwork and put it into a suitcase and send it to Mexico. And at the same time, Architecture Extrapolated, had a lot of experience working with the craft persons of Mexico City. It's not easy to cast concrete, particularly upside down. And so there was a lot of skilled labor, and also the concrete recipe and so on. So it's a good mix of like digital technologies with like traditional craftspersons, and also considering shipping logistics and so on. And also here's how things were concreted, like yeah, particularly, and also the formwork is very little, like just the edge beams, and the rest is stretched fabric, and it's lost formwork. So so that's the kind of example what we mean by architectural geometry, because ahead of time you already think of like logistics, you ahead of time think of construction, ahead of time think of structural performance, and so on. Similar example here for a commercial project with Zaha Hadid Architects for a gallery for mathematics. Everything that you see in this image is considered similarly, that the benches, the flooring, which is like a single pour resin flooring, all the objects here, even though they're all custom made, they're made more cost effective because like we consider ahead of time like the entire process. So the same kind of thinking goes from design conception, like all these complex geometry surfaces, in down to the tailoring of the seams and the boundary conditions and so on. And it also is super advantageous to deploy such geometric complexity even in like very relatively technologically poor conditions. For example, we were able to use the same technology and the same kind of design thinking here for a school for refugee children, which was again made within 2 months and before the winter rolled in, and so on. So and so we're now trying to do similar kind of thinking with 3D printing. How can we think of 3D printing in a geometric way? And also think of 3D printing on the right as a kind of scaled down version of masonry. And so you can see every culture knows how to make masonry. And there's like very simple geometric rules to understand masonry structures. And if you scale that down and make some modifications, you can begin to understand this 3D printing, particularly in concrete. And so because it's a layered construction, we are also from the ground up, like rethinking how to represent the geometry. You know, can we use like image-based technologies rather than other standard BIM representations, like particularly NURBS or meshes? So we're kind of thinking, how can we represent all of these layers by just representing or using a bunch of images like an MRI scanner, as opposed to representing all of this detail like in other heavy formats. And so therefore it's also like directly related to the fabrication process, because the machine that prints it needs to know the information of every layer. And so it's again structurally related to masonry, construction wise it's related to masonry, and so on. And another advantage for such rethinking everything is because in this case is that it's very easy to create complex geometry. So for example, in this object on the right is created with simple inputs. All you have to do as a designer is provide these circles and these red lines, and the blue is the outcome, is automatically created by these simple inputs. So the additional benefit of that is like you can go from like the design software to manufacturing and both of them are like 500 kilobytes each. And you can create this object in 2 minutes, and then you can check it in another 10 minutes and then start printing. So that's the general another benefit of such kind of rethinking the entire workflow, being lean from the software point of view. And another benefit of structure thinking about geometric thinking is that it can incorporate a lot of historic knowledge built into like these cathedrals and other civic buildings, which was entirely geometrically captured. So there was no numerical calculations. So all of the sustainable aspects about this kind of stone construction is because of its geometric nature of these ribs and how material is arranged geometrically. And the same, so my PhD advisor, Philippe Bloch, and his research group, they're incorporating all of these ideas from cathedrals and so on, adding new layers of computation and saving a lot of material and also saving a lot of space. So it's 70% lighter, 25% thinner floor slab. So these are the key aspects of architectural geometry, a geometry-based way of thinking about structure and construction. And it's scientific, it's exciting, it's novel, it's fun. It's very entrepreneurship friendly. It's historically continuous, so it's unlike modernism, unlike other aspects of the 20th century, which got rid of a lot of historic knowledge. This one is actually picking up on all the things that were developed over hundreds of years. And it is increasingly proving to be ecologically sustainable because you're using a whole lot less material in the first place. Even if you use concrete, you're using so little of concrete because of the structural strength coming from the geometry. So after Nit Candela, we're not only making these kind of pavilions, we are definitely enthusiastic and highly optimistic of a mainstream future for these kind of rethinking. We are currently just our small team of 10 people. We're doing a stadium, we're doing 6 metro stations, we're doing mixed use towers and so on, which currently I cannot really speak about, but they might be become visible in the press by the end of the year. So we are extremely optimistic, but what I can actually talk about is another aspect where we are optimistic is that we can transfer all of these learnings from a research environment into a more democratic setup, into prefabricatable building components, plus mobile and digital factories. And also all the geometric knowledge is now beginning to be transferred into a kind of democratic platforms like game engines. It's available on a browser through web services. And so therefore it's encouraging kind of end user participation. So one of the projects, so again, with our students at the Architectural Association, what we are now thinking is how we can leverage video game technology, how we can leverage Facebook to do good things, how we can build communities, online communities first, where people can think about housing and they can leverage all of these new digital manufacturing technologies, but focus on what they want. So these are just kind of blue sky sketches, let's say, where we are making these little apps and allowing for people to participate and choose their house or things like this. So ultimately, that what we want is to be able to offer all these kind of all these customization choices, not only in the shapes, but also in the kind of spaces that they want, communal spaces, private spaces, sharing spaces, and so on. So to build on top of the promise of industrialized construction, all these user choices, so that so that the construction side is taken care of, and we already know the technology is there and it's available. So we're just combining available technologies with participatory technologies like the game engine, like Facebook, like the phone, and so on. And so we are seeing beginning to see the first applications of this kind of blue sky thinking from academia. We're working with, so we are thinking of video games as kind of aggregating these components, which is again not particularly a new idea, but we are also saying that we can aggregate within that other things like other geometries, curved geometries, which are known to be structurally effective, which are materially effective, But so far we're kind of cost prohibitive because there was no manufacturing technology. So that's increasingly changing. So we want to incorporate that already into video games. In other words, like, you know, all of these research ideas, like the floor slab, like the kind of concrete benches that we're now making for only exclusive clients, we can begin to make all of these things available through democratic software toolchains. So this is our first kind of commercial project where we are literally trying to do that. This is a project in Honduras, which will go live by the end of the month, where we are thinking, you know, we can bring machinery like in a we're actively exploring this aspect of how we can import machines rather than import prefabricated boxes, and see and layer on top of that like user choice, where the users can choose all kinds of things about the arrangement of their house, and so they can pick these pixels, and all of these are kind of already computed, not only the shapes but also the costs, and so on. So they can pick between 1 to 5 pixels, and they can pick any of these options. And these are only a tip of the iceberg. Like there are like hundreds of options that can be, hundreds of combinations that you can think of. And then combining that with this kind of standardized construction systems with some bespoke construction. So we're thinking like how to convert raw material all the way to the house. And so, you know, so in the end, like the user is only concerned about their house. They don't have to worry about all the logistics and so on. So, and so that's like our outlook, and that's like really what keeps us super enthusiastic and hopeful of the near future. And another thing that keeps us extremely positive is that all of this has actually been done before. And it used to be called the Bauhaus. And between the 10 years that they were operational, 10 or 15 years, and they had this kind of 100-year impact, you know, they explored exactly all of these technology of knitting, of origami, and so on. And like all of these kind of got manifested in these kind of showcase buildings of the 1950s. And at the same time, it also affected all the housing efforts in the 70s and so on. So we're trying to reconnect with modernism and also prehistory, like people like Gaudi and so on. So with that, like I will leave, uh, leave it there, and like I'm happy to answer any questions. Thank you for your attention.